Welcome back for another lecture. In this lecture, I'm going to show you how we can very simple way can calculate PCA or principal component analysis. So suppose we have a matrix V, which is here, and we're going to assume that it is standardized or its mean is 0. So its singular value decomposition is phi sigma phi transpose. And then if we calculate the covariance of this matrix, which is here, and we can write in terms of a singular value decomposition, then we get these quantities. So because you have the matrix V decomposed in singular values and singular vectors, those are 3 vectors. You transpose V here, so every component get transposed, and then you end up with this quantity here. So it shows that the covariance matrix is kind of related to the left singular vectors and singular values. And if we now take the eigen decomposition of the covariance matrix C, we will definitely get the eigenvectors are phi, which are the left singular vectors of the matrix. So then I can immediately conclude that the principal components of the matrix V are given by phi, or the scores are given by phi. We can multiply by V with phi, which is the score. So phi are principal directions. If I multiply V with phi, I get the scores, and the scores are given by phi times sigma. So that's a straightforward calculation. Let's take a look at an example in Python. So I have a very simple random data set called ingredients.csv, which is here, that I have read it with this numpy command, and then let's see if I plot that. How does it look like? So here are the data set is very much random, and it is not centralized. Okay, so what I will do here first, I will centralize this data. So I will take one thing is I will first check here. I'll first tell you that the data set are kind of very random, and what I have put here, every column is a variability. If I every column is a variable, and if I go by row wise, then I have the features or variability. So the first thing is let me first transpose this matrix. So U equals U dot T. So the idea is that we will have each column of the matrix is a measurement, and then the next column is another measurement, next column is another measurement. So then if I go by column wise, then I will get kind of features of the data, and if I go by row wise, then I get my variables. Okay, so what I will do here is I will take the mean. So np dot mean of U, and I will go by column. So x is equals 1, and I will keep the dimension, keep times equal to 1. Okay, and then you take that value and call this U bar, for example, and then you subtract. So B equals U minus U bar. And now if I plot that B, something wrong. Yeah, that is double. Okay. Okay, so this time the data looks like little different. Is because of two reasons. One reason is I transpose the data. So let's try. Yeah, so I have the data set here, and this is now this time centralized. You can see that it's going from minus 0 to something positive, sorry, 0 to something positive, 0 to something negative. Well, axes are not kind of adjusted. That's okay for the purpose of PCA calculation. Let's just comment out those two lines. I don't need that. Okay. So the idea is we want to do the singular value decomposition. So in Python numpy command, we can use so phi comma sigma comma psi transpose, those three matrices. np dot lin lg dot spd v full matrices equals 0. Okay, so let me tell you what is on line 10. So numpy provides a linear algebra package which is linlg, and this linear algebra package has a spd command. So np.linlg.spd, that's the syntax to calculate spd. The first argument is my matrix, and the full matrix equals 0 tells us just to do the economy mode. So the redundant zeros, unnecessary zeros to be removed. Okay, so that's the command. So the first element here, phi, is the mathematical phi sigma and psi transpose. So I just use, because numpy returns the matrix as transpose to indicate that I put psi psi t to indicate that this is a transpose. Okay, so now we can print, for example, phi. See how does it look like. Okay, let me see if my screen is visible. So let's just do it again. Okay, so those numbers are my principal components. So let's look at the code again. So you can see that the code is straightforward. In line number 4, I read the data. Line number 6 is not necessary. This data was intentionally put it in a different way. So I transpose it to ensure that all rows are features, and every element in column wise will be the vector. So this is something, if we store it that way, particularly in fluid mechanics, we can have a time snapshot of my data. So the time snapshot can be in a column. So for example, if you have some students marks on different subject wise, so marks of 10 students on physics, chemistry and math. So the marks will be kind of features, and physics, chemistry, math will be kind of variability or the variable. So then if we put each row as physics, first row as one row is physics, another row is mathematics, another row is say chemistry. So then I will have column wise, for each column I will have a variable, and then I will see the variability if I move column wise. Okay, so that's a kind of something helpful to do the calculation. Okay, then line 7, I calculate the mean. So this is just a numpy command suitably. I calculate the mean, and on line 8 I subtract the mean, and then you calculate the singular values phi sigma psi transpose, and the phi is your principal compounds. After that, what analysis you want to do, that is up to you. This is the steps for principal component calculations in using numpy SVD command. Thank you very much.